Hello, and welcome to this presentation on exponential functions. This presentation does assume you are familiar with the definition of a logarithm and the use of logs. The exponential function is one that contains the e to the x term, where the e, the exponential, is 2.7183 to 4 decimal places, although it's actually an irrational number. A plot of the e to the x curve looks like this. This is e to the x here, and we've also plotted here e to the minus x curve. These exponential functions can model things like naturally occurring phenomena such as population growth or spread of bacteria, radioactive decay, pressure change with altitude, capacitor discharge, expansion of metals, or cooling characteristics. And we'll be looking at some of these examples in this presentation. The first thing I'd like to do is to get us familiar with using the e to the x function on the calculator. There are several ways of finding the e to the x values. We can use the calculator, a power series of e to the x, and even tables of exponential functions. But here I just want to use the calculator. So in exercise 1e, we're just going to use the calculator to find the following values. So on your calculator you will find an e key. It's usually shift ln key. Ln is a natural log key. Well, my calculator is shift in ln, and I will get the e function. So to find the value of e to the power of 0.15, I would do shift ln, that will give me the e function, and I just put 0.15 against it. Different calculators have different ways of approaching this. I suggest you make sure you're familiar with yours. What you should find is e to the 0.15 should give you a value of 1.1618. In other words, that's a 2.7 etc. e function raised to the power of 0.15. Type on your calculator e to the power of minus 0.314, you should get the value of 0.73053. If you type the value of e to the power of 8.67, again you should get a value of 5825.5. I suggest you have an attempt at those questions and become familiar with using the e key on your calculator. Exercise 2e here, we're using the calculators again to evaluate the parts A and B of this exercise. So part A, we're asked to evaluate 0.0356 multiplied by, in brackets, e to the 5.21 take away e to the 2.49. So on most modern calculators you will type in 0.0356. Some calculators need the times and some don't. I put a times in here and open a bracket, and you'll put e to the 5.21 take away e to the 2.49. And you can normally write it as it's typed there on the screen. That should give you 6.0888. On my particular calculator I have to type it in this format, 0.0356 multiplied by, in brackets, and my exponential is e, and then it's against the bracket of 5.21 take away e function again against the bracket of 2.49. That's the way I input it on my calculator. Gives you exactly the same value there. I would suggest you get familiar with the way you enter this calculation on your calculator. Exercise 2e here, part B. We're asked to evaluate 6 times, in brackets, e to the 0.25 take away e to the minus 0.25, or divided by e to the 0.25 plus e to the minus 0.25. That's written on one line there. On most modern calculators you can use a 2-line display, so you might type in 6 open bracket e to the 0.25 take away e to the minus 0.25 on the top line, and on the bottom line e to the 0.25 plus e to the minus 0.25. That gives you 1.4965. Again, different calculators have different formats. On my calculator I would type it in as shown here, very similar format, but it's all on one line. Notice the way I've got to use the brackets around my powers of e there to make sure the function works properly on the calculator. So again, if you're using my kind of calculator, one-line display, you need to type it in like that, but you'll get exactly the same answer. Again, I would encourage you to make sure you're totally familiar with typing in those kind of functions on your calculator. Exercise 2e is shown again here. All I'm doing in this particular slide is showing you the actual values for the exponential functions, just in case you have any trouble calculating the values. So this would be here, for example, e to the 5.21. This would be e to the 2.49 here, okay? Down in the part B here, this would be e to the 0.25. This would be e to the minus 0.25. I'll just let you use that as a backdrop in case you're having trouble working out the actual values. Okay, exercise 3E is a very similar kind of question to the previous exercises. It's just that it's actually given us a little context here. It relates to bacteria growth, and we're given an equation that B is equal to B0, a constant, multiplied by e to the power of kt, where k is a constant and t is time in this case. We're given the constant k is 0.2878, and we're given the value of B0 is 10 bacteria. We've got to use the equation to find how many bacteria would there be after t is equal to 5 minutes and also after t is equal to 60 minutes. So using the equation given, B is equal to the B0 e to the kt, we know that B0 is equal to 10 from the question and the k is equal to 0.2878. So for the first part of the question, when t is equal to 5 minutes, we simply put the value of 5 into the equation and work out the value of B. I'll let you do that on your calculators, same kind of thing as in the previous exercises. Part 2. All we're doing now is changing the time t to 60 minutes and again working out the value of the bacteria. Notice in this exercise how significantly the bacteria has increased between the 5 minutes and 10 minutes duration. So when people talk about the exponential increase of a quantity, you can see the kind of things they're referring to, this exponential growth. Exercise 4E, another descriptive question. This time it's electrical context. We're given the instantaneous voltage V, little v in this case, in a capacitive circuit related to time t, is given by the expression little v is equal to the big V multiplied by e to the minus t divided by CR. So the V, C and R are constants which we're going to be given. We've got to find V, to four significant figures here, when t is equal to 15 and that's milliseconds, so be careful of that. The capacitance is 20 microfarads, so be careful with that. The R is equal to 25 kiloohms, again be careful with that. And V is equal to 150 volts. So we need to be careful of the prefixes here when I extract the information from the question. So we're given the formula, little v is equal to big V multiplied by e to the minus t divided by CR. From the question, big V is equal to 150 volts. The capacitance, C in this case, is 20 times 10 to the minus 6 farads. That's microfarads, 10 to the minus 6. The resistance is 25 kiloohms, so that's 25 times 10 to the 3 ohms. And the time was 15 milliseconds, that's 0.015 seconds. So again, be careful with the SI prefixes. So what we're going to do now is put these values into the equation given. So little v, instantaneous voltage, is equal to the big V times e to the power of minus t divided by CR. So 150 is the big V, and that's multiplied by e to the power of, now I've got minus 0.015, and that's divided by the 20 times 10 to the minus 6, which is times by the 25 times 10 to the 3. Notice I've used a bracket there. Be very careful how you type this in on your calculator. I must have that second bracket there to make sure the bod mass is correct in this case. That then gives me 150 times e to the power of minus 0.03, and then doing the evaluation on that, I get the value of little v is equal to 145.6 volts. Again, I would encourage you to work through that carefully to make sure you clearly understand how the evaluation has been undertaken. I said previously we use the exponential functions for considerations such as evaluating the laws of growth or decay. Functions like this here, the y is equal to a times e to the minus kx will give you this kind of function, or the y is equal to a times open bracket 1 minus e to the minus kx gives you that kind of function. These curves can relate to laws that occur frequently with engineering and science, examples of quantities related to naturally occurring phenomena. Table 2 over the page will show you some illustrations. Table 2 lists examples of quantities that are related to the natural law with the exponential function. So things like linear expansion has an exponential function in it, change in electrical resistance with temperature has the exponential function in it, tension in belt drives has exponential function in it, laws of cooling, exponential functions, and so it goes on. All these expressions here, all these quantities relate to the exponential function. Just going to recap the definition of a logarithm here. This is the definition of a natural logarithm, specifically for the exponential functions. If we have y is equal to e to the x, e being our base, that would be called exponential form, we can write that as x is equal to ln of y. That's a logarithmic form. So we'll be using this relationship in some of the questions we're going to look at. What you'll find in some of the questions is the natural log, ln, or log to the base c, will be used in the calculations because e and ln are the inverse functions of each other. So in some questions they're both used to solve the problem.
Example 1x. In this example, we're going to rearrange an equation to make a variable the subject, and we'll be using natural logarithms as we go through the process. The formula for a product P, moles per centimetre cubed, in a chemical process is given by P is equal to 4.8 times open bracket 1 take away e to the minus 3t, where t is the time taken in minutes. If after the process is started the value of P is found to be 2.4 moles per centimetre cube, we've got to find the time taken, little t. So from the question we're given the formula P is equal to 4.8 times by 1 minus e to the minus 3t in brackets. We're told P is equal to 2.4 in this particular instance. So on the left hand side of the equation I've got 2.4 equals the 4.8 times the 1 minus e to the minus 3t in the bracket. What I'm going to do now is rearrange the equation to make t the subject. To do this, first of all, I will divide both sides by 4.8. So 2.4 divided by 4.8 on the left hand side is equal to 1 minus e to the minus 3t. I don't need the bracket on the right hand side now. On the next line, I've added to both sides the e to the minus 3t to make it positive. So on the left hand side I get 0.5, which is 2.4 divided by 4.8, plus the e to the minus 3t, and that's equal to 1. On the next line, I simply take 0.5 from both sides to leave me on the left hand side with e to the minus 3t. That's equal to 1 take away 0.5, or simply 0.5. So now e to the minus 3t is equal to 0.5. And that's the position I need to get to. I need to get the exponential function, e to the minus 3t, on its own on one side of the equation, but it must be positive. It's very important it's positive because we're going to take natural logs in a moment of both sides of the equation, and you must take natural logs of a positive number. You cannot take natural logs of a negative number. So it's very important that e to the minus 3t is positive. So now, taking natural logarithms, ln's, of both sides of the equation, on the left hand side the e function cancels because the ln is the inverse function to e. So we simply get on the left hand side minus 3t. Taking ln's of the right hand side, we get ln's of 0.5. Next line I'm simply dividing both sides by minus 3 to leave me with t on the left hand side. ln of 0.5 is minus 0.6932, and that's divided by minus 3. That gives us a value of t is equal to 0.231 minutes. Again, I reiterate, the main thing there was to transpose the equation to get the exponential function on its own on one side of the equation, and it must be a positive value.
Exercise 1x. In this exercise we're going to be asked to use the ln function, or the log to the base e function, to solve the problem. We're given an equation, r is equal to 0.42 times by s divided by L times by log to the base e of d2 divided by d1. This relates to an insulation resistance of a piece of wire. We're asked to find the value of r given that the s constant is 2000, L is equal to 120, d1 is 0.2 and d2 is 0.3. So this is an evaluation exercise. We're just going to put the numbers into the equation. So given that r is equal to the 0.42 times s divided by L multiplied by the ln, the natural log of d2 divided by d1. So putting the numbers in, 0.42 multiplied by the s, which is 2000, divided by the 120 for the L, multiplied by the log to the base c of d2, which is 0.3, divided by d1, which is 0.2. Make sure you put the values in the right order there. Multiplying 0.42 times 2000 divided by 120 gives me 7, and then that's multiplied by log to the base c of the 1.5, the 0.3 divided by 0.2. Doing the evaluation on that, we find that r is equal to 2.838 ohms.
Exercise 2x. In a capacitive circuit, the instantaneous voltage across the capacitor is given by the expression little v is equal to big V multiplied by 1 minus e to the minus t divided by CR in brackets, where the big V is the supply voltage, R is the resistance, C is the capacitance, and T, little t, is the time in seconds. If big V is equal to 200 volts, R is equal to 10 kiloohms, be careful of the prefix in a moment, and C is 20 times 10 to the minus 6 farads, we've got to calculate the time when the voltage, the instantaneous voltage, little v, will be 100 volts. So basically in the question here, we're given little v, the instantaneous voltage, we're given V, the maximum voltage, we're given C, the capacitance, and we're given R, the resistance. Notice I put that as 10 times 10 to the 3 ohms because of the kiloohms. I've also worked out here the product of C times R, which is 20 times 10 to the minus 6 multiplied by 10 times 10 to the 3, giving us a value of 0.2, just for convenience of using it in the calculation in a moment. So given little v is equal to the big V multiplied by the 1 minus e to the minus t divided by CR, I'm going to rearrange my equation now to make the exponential term the subject. So dividing both sides by big V, on the next line I get little v divided by big V is equal to 1 minus e to the minus t divided by CR. On the next line I've added e to the minus t divided by CR to both sides to get it positive on the left hand side, and I've taken away little v divided by the big V to get it over onto the right hand side, but it's now negative. So I've got my expression e to the minus t divided by CR is equal to 1 minus little v divided by big V. I've now got my exponential term on its own on one side of the equation, and it's positive.
Exercise 2x continued here. I've just repeated this line for convenience. So e to the minus t divided by CR is equal to 1 minus little v upon big V. What I'm going to do now is take natural logarithms of both sides of the equation, so ln's of both sides. So on the left hand side I get ln of the e to the minus t divided by CR, and on the right hand side I get ln of 1 take away little v upon big V. Now what happens on the left hand side is the ln function cancel with the e function. They're the inverse of each other, so they cancel to leave us with the minus t divided by CR. Try and think of that as if we had 3 squared and then square rooted, we would end up with 3. It's the same kind of thing, inverse functions here. Ln is the inverse of e, so they cancel each other out, just as a square and a square root cancel each other out. On the right hand side I get ln open bracket 1 minus v divided by v. What I'm doing on the next line is multiplying throughout by negative CR. In other words, I'm removing a negative from the left hand side and I'm multiplying by CR to get rid of the CR on the bottom of the left hand side. So I get T is equal to minus CR, so I've multiplied the top here by the minus CR, multiplied by the ln 1 take away V divided by V. I suggest just think that step through for yourself about how I'm rearranging the equation to get T, the subject. All I do then is put the numerical values in, so CR we were told was 0.2, so it's minus 0.2 times by ln of 1 take away little v was 100 and big V was 200, and the rest of it is basic arithmetic here to find T is equal to 0.139 seconds. I advise you to look at the arithmetic and clearly understand how we've evaluated T. Exercise 2x here. This is an alternative approach than the previous slide where we use the algebraic rearrangement. What I'm going to do here is put the numerical values into the equations to begin with and then transpose it with the numbers. For some students this makes this an easier solution. I've repeated the values of little v, big V, C and R for convenience here, and also the product of C times R, which was 0.2. So what we would do now with this solution is put the values into the equation straight away. So we're given little v is equal to big V multiplied by 1 take away e to the minus t divided by CR. So on the left hand side I would get 100 for little v, on the right hand side 200 for big V multiplied by 1 minus e to the minus t divided by the 0.2 for the CR. On the next line I've just divided both sides by 200, so I get 0.5 on the left hand side is equal to 1 minus e to the minus t divided by 0.2. To get the next line, I've added to both sides e to the minus t divided by 0.2 to make it positive on the left hand side, and I've taken away 0.5 from both sides to make that 1 minus 0.5, 0.5 on the right hand side. And again, I've got the exponential function on its own on one side of the equation and it's positive. What I do next is take natural logarithms of both sides of the equation. So on the left hand side, the ln and the e cancel each other out. So I end up with minus t divided by 0.2 on the left hand side. And on the right hand side, I'm just taking ln of 0.5, which is a number I can calculate in a moment. On the next line, I've multiplied both sides by 0.2 to leave myself with minus t on the left is equal to 0.2 multiplied by ln of 0.5 on the right. On the next line, I've worked out the ln of 0.5, which is minus 0.6931. And on the next line, I've multiplied that by 0.2 to get minus 0.1386. Notice I've got a negative on both sides of the equation, so they cancel. So therefore, t is equal to 0.139 seconds to 3 decimal places.
Exercise 3x. We're given the resistance of an electrical conductor at temperature theta degrees C is given by the expression R is equal to R0 multiplied by e to the alpha theta, where alpha is a constant and the R0 is equal to 3 kiloohms and the theta is equal to 1400 degrees C. We've got to find the value of alpha when R is 5 kiloohms and also find the temperature theta correct to the nearest degree when the resistance R is 4.7 kiloohms. So from the question, we're given the formula R is equal to R0 e to the alpha theta, where R0 is 3 times 10 to the 3 ohms, that's 3000 ohms, 3 kiloohms. Theta is equal to 1400 degrees C, and the R for the first part of the question is 5 times 10 to the 3 ohms. I'm going to rearrange the equation to make the exponential function on its own on one side of the equation and positive, and I simply do that in this case by dividing both sides by R0. So R divided by R0 on the left hand side gives me e to the alpha theta. Now I take natural logarithms of both sides of the equation, so on the left hand side I get ln of R divided by R0, and on the right hand side I get ln of e to the alpha theta. Don't forget the ln and the e cancel each other out because of inverse operations. So on the right hand side I get alpha theta, and on the left hand side ln of R divided by R0. And I've called that equation 1. Exercise 3x continued here. I've just repeated the equation 1 here for convenience. For part 1 of the question, we've got to find alpha. So rearranging equation 1, alpha is simply ln of R divided by R0 divided by theta. In other words, I divided both sides by theta. Put in the values. R is 5000, R0 is 3000, so that's 5 divided by 3. So ln of 5 divided by 3 divided by 1400. Doing the numbers on that, we find that alpha is 340.6 times 10 to the minus 6 per degree C. I'll let you check the calculation. Part 2 of the question is to find the theta. Again, we're going to use equation 1 here. So now rearranging equation 1 for theta, we simply divide both sides by alpha. So theta is equal to ln of R divided by R0 divided by alpha. Put in the values. This time the R is 4.7, the R0 is still 3, and we're dividing it by the alpha, which is from the part 1 above. Again, doing the numbers on this, we find that theta is equal to 1318 degrees C. Again, I'll let you check the figures. Exercise 4x. In a laboratory experiment relating to Newton's laws of cooling, the temperature capital T in degrees C is given by the formula T is equal to T0 multiplied by e to the minus kt. That's little t at the top. T0 is given as 62.3 degrees C, T is 22.5 degrees C, and time little t is 75 seconds. We've got to calculate the constant K in the equation. So given that T is equal to T0 e to the minus kt, we know the value of T and T0 and little t the time. We're going to rearrange the equation for K. So dividing both sides by T0, we get T divided by T0 is equal to e to the minus kt. Again, I've got my exponential term on one side of the equation on its own and it's positive. So now I take natural logarithms of both sides of the equation. On the left hand side I get ln of t divided by t0 is equal to ln of the exponential function. Don't forget ln of e cancel each other out because they're inverse operations. On the right hand side I simply get minus kt. On the left hand side I get ln of t divided by t0. All I've done on the last line is simply swap the terms around. So minus kt is equal to ln t divided by t0. Exercise 4x continued. I just repeated this top line for convenience from the previous slide. Now I'm going to rearrange the equation to make k the subject. To do that I divide both sides by minus t. Divide the left hand side by minus t and I get k. Divide the right hand side by minus t, I get minus ln of t divided by t0 all divided by t. On the next line I'm going to put the numerical values in, so minus ln of the t, 22.5, divided by the t0, 62.3, and that's all divided by the time of 75 seconds. The rest of it is arithmetic, which I'll let you review. You should find the answer for k is equal to 3.581 times 10 to the minus 3 per second. I would encourage you to review the arithmetic and make sure you understand how k has been found. Example 1f. This is a slightly different problem to those we've had on the previous slides. On the previous slides all the problems had exponential functions in the original equation. We rearranged these equations to get the exponential function on one side of the equation positive, and then we took natural logs of both sides of the equation to solve. In this question we're actually given a function with the natural log to the base e, in the original question. So what we're going to do here is rearrange the equation to get the log to the base e, the natural logarithm, on one side of the equation and positive, and then we're going to take exponential functions of both sides of the equation to solve. So a slightly different process in that we're going to take exponential functions of both sides here. In all the previous questions we took natural logs of both sides. So given the equation t is equal to r multiplied by log to the base e of a divided by a minus b in brackets, we've got to find the value of b. We're given that t is equal to 25.65, r is equal to 28, and a is equal to 5. So from the equation given, t is equal to r multiplied by log to the base e, ln, of a divided by a minus b in brackets, I simply divide both sides by r to get the log function on its own on one side of the equation and positive. So simply dividing the left hand side by r, I get t divided by r is equal to log to the base e of a divided by a minus b in brackets. So what I do now is take exponential functions of both sides of the equation. So on the left hand side I get e to the power of t divided by r, and on the right hand side I get the exponential function and the log function, which cancel each other out. So e of the log function cancel each other out because they're inverse operations. So I simply get left with, on the right hand side, a divided by, in brackets, a minus b. On the left hand side I get e to the power of t divided by r. So note that the e in the ln function, e and the log to the base e in this case, have cancelled each other out here on the right hand side. Example 1f continued here. I just repeated the top line for convenience. What we've got to do now is rearrange the equation to make b the subject. So the first thing I do is multiply both sides by a take away b in the bracket. So a take away b on the left hand side multiplied by e to the power of t divided by r. And I must have the bracket around the a take away b here. That's equal to a on the right hand side. On the next line I simply divide both sides by e to the power of t divided by r. So I get a minus b on the left hand side, don't need the brackets now, is equal to a divided by e to the power of t divided by r. On the next line I simply add b to both sides just to make the b positive. Adding b to both sides I get a is equal to the a divided by e to the power of t divided by r plus the b. On the next line what I've done is actually taken away from both sides the a divided by e to the power of t divided by r, but I've turned the equation around here to get the b as a subject on the left hand side. So b in this case is equal to a, take away a divided by e to the power of t divided by r. I'll give you a moment just to think that step through for yourselves. Now what I do is put the numerical values into the equation. In this case a is equal to 5, so it's 5 take away 5 divided by e to the power of t, which is 25.65, divided by the r, which is 28. I'll let you work through the rest of the steps on your calculator there, and you should find that b is equal to 3.
If you're having trouble following the algebraic approach that I've used to rearrange the equation for b, what you could do is go back to the top line here and actually put in the numerical values here for the a, for the t and the r, and you'll find it simplifies the equation slightly. It might help you transpose it in a more easier fashion. Okay, I'll leave you with some exercise on natural logarithms to attempt. In exercise 1f, you're given the equation r is equal to 0.42 multiplied by s divided by L, and that's all times log to the base e of d2 divided by d1. You're given some values in the question. You're going to have to rearrange the equation for d2. So the first thing you need to do is divide both sides by 0.42 times s and multiply both sides by L, and that will leave you with the log to the base e function on its own. From there on, you can take exponential functions of both sides and solve for d2. Exercise 2f, again you're given an equation, mu is equal to 1 divided by theta all times ln of t1 divided by t2. This is a belt drive problem. Again, you need to rearrange the equation to get the ln function on its own. So in this case, multiply both sides by theta and then take exponential functions of both sides and solve in this case for t2. Further question, exercise 3f here, you're given an equation t is equal to minus 1 divided by k multiplied by the ln of tt minus c all divided by t. In this question, again, you need to rearrange to get the ln on its own. You simply multiply both sides by minus k. We'll leave you with the ln function and then take exponential functions of both sides of the equation. I hope this has been of help to you. Thank you for viewing.